Well, thank you for the invitation. So, Weinstein Morse functions are the symplectic analog of Morse functions, and well, Morse functions are very useful in classical smooth topology, proving things like H-cobordism theorem. And the goal of this talk is to see to what extent those results hold in the symplectic setting, to what extent we can manipulate these Weinstein Morse functions. And the talk is going to be mostly high-dimensional symplectic geometry, but I'm going to explain where the proofs break down in low dimensions and kind of say what the contrast is. Okay, so let me begin with some background. So I'm going to use the equivalent language of Weinstein handle bodies, but a Weinstein Morse function gives a Weinstein handle body. So suppose M is a exact symplectic manifold with contact boundary. And in addition, you have an isotropic sphere lambda in the contact boundary. So there's also some framing data on lambda, but I'm not going to focus on that. The isotropic condition implies that k is less than n, where 2n is the dimension. And then Weinstein showed how to get a new symplectic manifold, so which I'll denote by M union a handle. So this is a new exact symplectic manifold, again with contact boundary. So this is called Weinstein handle attachment. So the picture you should have in mind is you have M down here, it's contact boundary, you have lambda, and then you attach a handle like this. So lambda is the attaching sphere. And then over here you have the belt sphere of the handle, which is a sphere in the new contact boundary. And then over here you have this disk, which is the co-core disk. And the nice thing about this Weinstein handle attachment procedure is that it can be iterated. And there's a natural class of symplectic manifolds that you get by iterating this procedure. So a Weinstein domain is obtained by successive Weinstein handle attachments to the ball with the standard symplectic structure. You can think of this as just a zero handle. So this actually turns out to be a pretty large class of symplectic manifolds. I'll give some examples in a second, but the point is that their symplectic topology is just determined by the symplectic topology of these attaching Legendrians. So if you understand the attaching Legendrians, you understand everything about this domain. It's kind of a more concrete way of presenting symplectic manifolds. So examples, take a smooth manifold and take its cotangent bundle. If you take a smooth handle body presentation for M, you get a Weinstein handle body presentation for the cotangent bundle. Also, affine varieties, surfaces with boundary. So already a large class of symplectic manifolds. And maybe you care about closed symplectic manifolds. Well, it turns out that every integrable, or any closed symplectic manifold, where the symplectic form is integral, has a symplectic hypersurface such that the complement is Weinstein. So my Weinstein domains are important even if you care about closed symplectic manifolds. Okay, so that's what a Weinstein domain is, and here I've defined it as a fixed presentation. But there's certain moves you can do to change the presentation. So these are called Weinstein homotopy moves. And well, the first move is kind of obvious. You can just move the attaching sphere in the contact manifold where it lives, through isotropics, through embedded isotropic spheres. The second move is that you can change the order of attachment of handles, but this is only possible in certain situations, and that's when the belt and the attaching spheres are disjoint of the two handles. So the picture you should have in mind is, okay, I first attach one handle like this, and then I have another handle that I attach afterwards. And so here's the attaching sphere of this one, and here's the belt sphere of this one. Because they're disjoint, I can push this handle down, and it doesn't get trapped by this handle because it's disjoint from the belt sphere. And so I can change the order like this. So I can first attach this handle, and then I attach that one. So in particular, I can assume that the presentation is self-indexing. The lower index handles are attached first, and then as the index increases, I attach the handles with higher index later. So the last move is I can create or cancel pairs of handles of consecutive indices if the belt and the attaching spheres intersect in a single point. So the picture is, suppose I have a one handle, and then I have a two handle. Here's the attaching sphere of the two handle, and it hits the belt sphere once, and then I attach this two handle, but this is really like a half disk, so I can push this whole pair down and cancel them, and I get no handles. And so that's canceling the handles, and then going this way is creating the handles. Okay, and so these are exactly the same moves as you would do for a smooth handle body. The main difference is for move number one, you're required to move through isotropics. And so the question is, what does this actually mean about the possibilities for the handle bodies? And let me mention one more move, which is really a combination of two other moves. So it's called the handle slide, and this is a combination of 1 and 2. But it's going to be the one that we're going to use, so I thought I would emphasize it. So what goes on here is you have two handles of the same index, and you look at the new contact manifold after attaching this handle, and you view this sphere in that new contact manifold, and you start sliding it over. So it starts going over this handle, and then it eventually engulfs the handle. So, like so. And then it's back, and now the attaching sphere is back down to the original contact manifold. So in terms of the attaching spheres, you have these two attaching spheres, and then the new attaching spheres, this one stays the same, and then the second one is the connected sum of the two. So the point is, even though these two links are not isotopic even smoothly as links, the domains you get are the same. So let me say that precisely. So there's actually a theorem of Chiliback and Eliashberg. Says that Weinstein homotopic Weinstein domains have symplectomorphic completions. By completion, I mean you add an infinite cylindrical collar to this compact domain, and you get an open symplectic manifold. But basically, you should think that the domains are symplectomorphic, that all of their symplectic invariants are going to be the same. So you do these moves, and you don't change the symplectic topology. Okay. So there's a natural invariant you can associate to Weinstein domains up to Weinstein homotopy. It's called Weinstein complexity. And so the following definition is due to Abuzaid and Seidel and Eliashberg in the Stein case. So the definition is kind of denoted by W crit, is that it's the minimum number of handles in, so W is a Weinstein domain. It's the minimum number of handles in a homotopic, in a Weinstein homotopic handle body presentation. So you start with some presentation, and you do these moves. You can create more handles, you can kill handles, and what's the minimum number of handles you get? So tautologically, a Weinstein homotopy invariant. And there's a corresponding smooth notion, which is just crit of W. Oh, by the way, I call it crit because it's also the minimum number of critical points of a Weinstein Morse function, which I didn't really say what it is, but it's something that gives you a Weinstein presentation. So crit of W, now you forget that W is a Weinstein domain, you just think of it as a smooth domain, and it's the same thing, but it's in a smoothly homotopic, smooth handle body. So it's the same moves, except for move number one, you're allowed to move just through embedded spheres. The spheres don't have to be isotopic. So W crit has to be at least as big as crit of W, because any Weinstein presentation gives a smooth presentation. And let me just mention that this is kind of a very classically studied invariant. This is, Morse showed that this is at least the number of generators for integral homology of W. And one interesting thing due to Smale is proof of the H-cobordism theorem is that this is a equality if so if n is, okay, I guess if 2n is at least 5 and the manifold is simply connected. And so you might ask, when is this an equality? That's going to be the focus of this talk. So there's a theorem of Mark McLean. So he showed that there exists infinitely many, well, actually, there exists an exotic Weinstein ball So it's a Weinstein domain that's diffeomorphic to a ball for n at least 4, such that the standard structure and this exotic one and also the exotic one boundary connect sum, the exotic one, this is attaching a one handle between two disjoint copies, such that all of these boundary connected sums are all non-symplectomorphic, or the completions are not symplectomorphic. So that implies that by this theorem of Chiliback and Ilya-Ashberg, that they're not Weinstein homotopic. And in fact, so W crit of this exotic Weinstein ball is at least 3. So it has to be odd just by Euler characteristic reasons. But if it had only one Weinstein critical point, one handle, like a 1-0 handle, you could somehow contract the whole symplectic manifold to a neighborhood of that ball, but the ball has a standard structure, and so the whole thing would be standard. But by this result, they're not standard. And they're not standard because of some symplectic invariant symplectic homology. So this is at least 3, and so that means this inequality over here is strict, at least in some cases. And a priori, it's not clear what W crit is. It's not clear how it behaves when you take boundary connected sums. Is it bounded? Does it go off to infinity? So that was originally not clear. Let me mention some other results. So Abuzid and Seidel, they found different exotic Weinstein balls, just infinitely many exotic Weinstein balls, where K is indexing the infinite collection, such that W crit is bounded. So in those examples, it wasn't clear. Abuzid and Seidel showed that there are examples where this is actually bounded. There was another later work, joint with Ilya-Ashberg and Ganatra, that there exist infinitely many now exotic cotangent bundles of spheres with W crit equal to 2. And this is the case of minimal complexity. This is the best you could hope for, because crit of a cotangent bundle of spheres 2. Just smoothly, you need at least 2 critical points to build up a cotangent bundle, and W crit is at least as big as crit, so it's at least 2, and in this case, those examples have 2. So those have minimal complexity. So this kind of suggests that there's examples with minimal complexity, and maybe the situation is not so bad. And the main result that I'm going to talk about is a generalization of these results, which actually implies this statement. And this statement, well, we'll see. So again, W is Weinstein, N is at least 3. This is the high-dimensional part of the talk. The W crit of W can actually be bounded by of W plus 2. So what does that mean? It means that W crit of any Weinstein structure on a ball, well, crit of a ball is 1. Smoothly, you only need 1 critical point. So this is, it's always either 1 or 3. So in particular, this non-trivial lower bound right here, this is kind of the only interesting lower bound that you need. Everything is either 1 or 3, and if you're 1, you're Weinstein homotopic to the standard structure. If you're 3, you're not. So, and if you have some restrictions on the smooth topology of W, you can actually do a little bit better. So if, say, the nth homology of W is not 0, then W crit of W is actually equal to crit of W. So basically, if you need an n handle just for topological reasons, then this can be an equality. In this case, you don't need an n handle for topological reasons, but as we'll see symplectically, you always will need an n handle, and so that's where this one is. Yeah, well, maybe I should mention, these 3 critical points have index 0, n minus 1, and n. And as I'll say later, all the symplectic topology can be captured by the n handles. So, yes. One thing this implies is this W crit, this cotangent bundle of a sphere is always 2, right? Because cotangent bundle of a sphere, it has non-zero nth dimensional homology, and crit of a cotangent bundle of a sphere is 2, and so by this second case, it's always 2. Something that this, let me say what this implies, you can consider Legendrians, which are maximal dimensional isotropics in the standard context sphere. You can use them to attach a handle to the ball, and you get some Weinstein structure at a cotangent bundle of a sphere. And this is saying that this map is surjective. So this map is given by Weinstein handle attachment. So here I have the standard ball, I have some crazy Legendrian, and here I'm attaching a handle to that crazy Legendrian. This is Weinstein domains up to Weinstein homotopy, and this is Legendrians up to Legendrian homotopy.
A question about dimension?
Yes.
So,
Here.
2n?
Yes.
So that's the 2n dimensional ball, right?
Yeah.
So the isotropics are up to dimension n minus 1, right?
Yes.
So you have written there 0, n minus 1.
But the handles are.
Oh, the handles.
Yeah. Yeah, the handles have one bigger index.
Yeah.
Or the dimension of attaching spheres. So let me mention that I don't know anything in dimension 4. Maybe as usual, but so let me question, is it true that W crit of a 4-dimensional Weinstein domain is less than crit of the smooth domain plus 2? Of course, this is also not well understood in dimension 4, but you could ask if this equality holds. Let me also say that the situation in dimension 4 is pretty different. Like, this theorem of Markov-MacLean is not true in dimension 4. There's only one Weinstein structure on the ball, on the 4 ball. So, okay, it's going to be true for the 4 ball just because there's only one. And there's other smooth domains that have only finitely many Weinstein structures. So there might be some bound here that's maybe depends on the smooth type, but it is a bound if there's only finitely many Weinstein structures. I think we don't know any examples of 4-dimensional smooth domains that have infinitely many Weinstein structures on them. If people know, I would be happy to hear. So that's dimension 4. Okay. Let me talk about the main tool, which are flexible Weinstein domains. So definition, the Weinstein domain W for n at least 3 is flexible if all index n handles are attached along loose Legendres. Okay, so now I have to define what a loose Legendrian is. Definition, Legendrian in some contact manifold, again, n is at least 3, is loose if lambda has kind of if it has a loose chart. So what that is a Darboux chart for this contact manifold, such that lambda inside that Darboux chart contains a zigzag like this, or a zigzag that's spun around. So again, so you require there to be some Darboux chart for the contact manifold, such that when you intersect that Legendre with that Darboux chart and look at the front projection, you're going to see a zigzag. Okay. So this definition is nice because of the following result of Murphy. So suppose lambda 1 and lambda 2 are loose Legendrians, and they're formally Legendrian isotopic. Then the result is that they're actually Legendrian isotopic. So, okay, to find what loose is, what does formally Legendrian isotopic mean? It means that they're smoothly isotopic, and then there's also a rotation of the tangent planes to Lagrangian planes. So this is basically an algebraic topological condition, whereas this is something very geometric. So this says that some topological condition implies something, or some algebraic topological condition implies something geometric. So this is not true for Legendrians in general. There's many Legendrians which are formally Legendrian isotopic, but not actually Legendrian isotopic. However, if you're in this class of loose Legendrians, then formally isotopic actually does imply Legendrian isotopic. And in particular, you could take any two Legendrians which are formally isotopic, add this zigzag to some small Darboux chart in each of them, and all of a sudden they become Legendrian isotopic. So this little zigzag, it somehow kills a lot of the symplectic information that's contained in the original Legendrians. So, so using this result, Chiliback and Ilyashberg showed that if W1 and W2 are flexible Weinstein domains, domains built up using these loose Legendrians, and they are formally symplectomorphic. Again, you see the corresponding words in this statement. Then they are actually Weinstein homotopic. In particular, the symplectomorphic. Formally symplectomorphic, I mean, you take two symplectic structures and they can be deformed to each other through non-degenerate two forms. But the two forms don't have to be closed the whole time during the isotopy. So again, something algebraic topological implies something geometric over here for this class of flexible domains. Again, there are domains, Weinstein domains, which are formally symplectomorphic, but not Weinstein homotopic. But for this special class, the statement is true. So, okay, some examples. V. The easiest example is all handles have index strictly less than n. So So that definitely satisfies the definition of flexible, because that's a condition on the n handles. And basically the idea is these handles also satisfy some version of this due to Gromov. And so they also have no interesting symplectic geometry. All the interesting symplectic geometry will be contained in the n handles. Okay. There's also a flexibilization procedure. You start with the Weinstein domain, and you associate a flexible Weinstein domain, which is formally symplectomorphic to it, but not necessarily actually symplectomorphic. And how does this work? Well, let me give an example. Suppose you're looking at the cotangent bundle of a sphere. What that is it's just a ball, so an index 0 handle, plus a single n handle attached along this. Okay, maybe this picture is not so good. I have a Legendre unknot, and I'm attaching a handle to it, and that's what the cotangent bundle of a sphere is. Now, the flexible version of that is just the same thing, but now I add this zigzag to this Legendre unknot, and I do it in a way that doesn't change the formal class of the knot. And this will actually be formally symplectomorphic to the standard cotangent bundle. So formally, but not symplectomorphic. So one way to see that is because symplectic homology of this domain doesn't vanish, whereas the symplectic homology of this domain vanishes. So again, these two domains are the same from the point of view of smooth topology and algebraic topology, but they're different from the point of view of symplectic geometry. Let me give another, maybe more subtle example. Well, we'll see. So again, I'm viewing, so this is, again, the front projection of the Legendrian, say in R2n minus 1, but I'm viewing that as the contact boundary of the ball. So this one is loose, and then I can have another one like this. And what I'm saying here is I start with the ball, and I attach a handle to this Legendrian, and then I attach a handle to this Legendrian. And this is actually, this is flexible. And the idea is, well, when I first attach along this one is loose, so that's flexible. But even after I've attached this one, the second one has a loose chart in the complement of the first one. So it's still loose, and so when I attach it, I will still get a flexible domain. On the other hand, if I draw this Legendrian, and then I draw its push-off, so I kind of draw this, so, and I attach two handles to this, this is actually not flexible. Even though each component of the link is a loose Legendrian, right? It has this zigzag. The problem is that each Legendrian is going through the other one's zigzag. Like when I attach a handle to this one, and then I view this second Legendrian in the new contact boundary, that is no longer a loose Legendrian. In fact, this domain has non-vanishing symplectic homology. So for us, the important thing is that the loose charts are disjoint from each other, or that the loose chart of the next one is disjoint from the loose charts of all the previous ones. So why am I talking about flexible Weinstein domains? So there's a theorem of Chiliback and Ilya-Ashberg. It says that if W is flexible, again, by this I mean n at least 3, then W crit of W is actually equal to crit of W. And the idea here is that, remember, the only difference between the smooth homotopy moves and the Weinstein homotopy moves was the smooth number 1. For the Weinstein case, you're required to move through isotropics, whereas in the smooth case, you can move through any embedded spheres. But if all the attaching spheres are loose, essentially you can realize any smooth isotopy by Legendre isotopy. That's the proof of this statement. Okay, so we mentioned theorem 2, which is that now if W is an arbitrary Weinstein domain, then it can be Weinstein homotoped to its flexibilization plus 2 handles. And this forms a Weinstein cobordism, and this is smoothly trivial. So this implies the main statement in theorem 1, that W, so this presentation means that W crit of W is less than or equal to W crit of W flex plus 2, that's these 2 extra handles, and while W crit of W flex is equal to just crit of W by this theorem of Chilibak-Eli-Ashberg, and this gives part of theorem 1. Let me just say explicitly what's going on here. First, you start with an arbitrary domain, W. You first homotope it to this flexibilization plus these 2 handles, and then you use this theorem of Chilibak-Eli-Ashberg to do a Weinstein homotopy to W flex to kill all the unnecessary handles. So there's a homotopy of the subdomain, but during that homotopy, you have these 2 handles up top, and they kind of just get dragged along. You don't have to create new handles during this homotopy. So, yeah, one remark is that there was a similar statement was proven by Eli-Ashberg and Murphy. They showed that they constructed a exact symplectic embedding with contact boundary of W flex into W. And so that's exact symplectic embedding, and so the complement is an exact symplectic cobordism, but it wasn't clear whether that cobordism has a Weinstein structure. Now this statement over here shows that there's actually a Weinstein embedding of W flex into W, and the complement has a Weinstein structure. But in addition, the complement has only 2 critical points. But I thought I would mention this existing result. And for dimension let me say what's known for dimension 4. So, another remark. So in this 4-dimensional case, then the proof of this is going to show that W is Weinstein homotopic to something I'll call V stabilized plus a single 2-handle. And this V stabilized is kind of the 4-dimensional version of flexible Weinstein domains. It's a Weinstein domain where all the attaching Legendrians have zigzags. I mean, these zigzags make sense in dimension 4 as well as they do in higher dimensions. And then there's a single extra handle here, kind of similar to this extra handle over here. But the problem is it's kind of unknown whether W crit of of this V stabilized is equal to crit of V stabilized. Like, it's unknown whether this result of Schillebeck-Lee-Ashberg is going to hold for these domains, and that's what I used for this inequality over here. But there is an analog. For example, this domain has vanishing symplectic homology, so there's some nice conditions. Okay, so now let me get to the proof. Of theorem 2. So first I'm going to prove something weaker. First I'm going to prove that W is Weinstein homotopic to some V flex plus a single n handle, where I don't have as much control over the topology of V flex as in this statement. In this statement, like V flex would be W flex plus a single n minus 1 handle. But so similar statement, flexible domain plus a single handle, which is maybe not flexible, but less control over the topology. So by move number 2 with the exchanging the order of the handles, we can assume that all the lower index handles are attached first, and then you have a bunch of n handles. So you can assume that W is W sub. So these handles have index less than n, and then there's some collection of n handles. We want all of these handles to be loose except for, say, the last one. And the key is going to be to use model for the handle slide model due to Castles and Murphy. So the statement is that lambda 1 or lambda 0 lambda are in some contact manifold. Lambda 0 is a sphere. So we're going to be handle sliding over lambda 0. And suppose there's a chart where lambda and lambda 0, a Darboux chart where lambda naught and lambda 0 and lambda look like this. They look like parallel Legendrians. Then what we can do is we can change the model. So we have lambda 0 here, and lambda becomes this other Legendrian. This is h of lambda 0 lambda. And the claim is that lambda is Legendrian isotopic to h of lambda in the new contact manifold obtained by attaching a handle along lambda 0. So lambda and h of lambda are not even smoothly isotopic in the original contact manifold. But once we attach a handle to lambda naught, they do become isotopic in the new contact manifold. This is exactly the handle slide that I was talking about before, and this h of lambda is, at least topologically, a connected sum of lambda and lambda naught. But if you want to know what it looks like as Legendrian, well, it has this cusp model right here. Okay. Yeah, maybe. Okay, so in particular, W, which was the subcritical domain plus all these other handles, is homotopic to the subcritical thing plus a handle attached along lambda 1, but then we attach handles along the handle slid, Legendrians. Right? This is just saying that after I've attached lambda 1, the other lambdas are isotopic to h of them, and so these two domains will be Weinstein homotopic. And finally, these are all m handles. They all have the same index. It doesn't matter which order we attach them in. So this is homotopic to W sub plus where we first attach these handles, and then we attach lambda 1 last. So we've handle split everything over one handle. That's what I'm saying here. Okay. So far I haven't really said anything about the proof. This is just the setup. But now, let me do an example, which I think will illustrate the proof. So, suppose you have some Legendrian, lambda 1. This is lambda 2. They might be linked. Lambda 3. So again, the idea is to handle slide everything over lambda 1. And, well, I don't know how they interact. So what instead I'm going to do is I'm going to do a local modification somewhere far away from where the Legendrians were originally. So I'm going to pick a separate Darboux chart, and I'm going to take a point of lambda 1, and I'm going to push it to that Darboux chart. So I just push the point of lambda 1. And then, same thing, I'm going to take a point of lambda 2, push it to this Darboux chart. And now I'm going to do a Reitermeister move. This is a Legendrian isotopy. So far I've just pushed lambda 1 and lambda 2 to separate Darboux chart. And now lambda 1 and lambda 2, they look parallel right here. And that's exactly what the input is for the handle slide model. So I'm going to use this chart over here to handle slide lambda 2 over lambda 1. So here we go. Look like this. Okay. And this is now h of lambda 1, lambda 2. And the point is that now h of lambda 1, lambda 2, it does have a zigzag. So here's this is the loose chart of h of lambda 2. You can see it explicitly. So in particular, h of lambda 1, lambda 2 is loose. However, lambda 1 is still going through the loose chart of h of lambda 2. So it intersects it, and so it's not loose, but not in the complement of lambda 1. Okay, and now I just repeat the procedure for lambda 3. Again, I pick a separate Darboux chart way out here. And it's important that the Darboux chart is different from the chart I picked for this one, because otherwise the two loose charts might interact. So I handle slide like this. Again, I do this Reitermeister move. I handle slide. This is h of lambda 1, lambda 3. Where lambda 1 is kind of this new version of lambda 1 that I've pushed. Of course, you can push the whole picture back to neighborhood over here. Okay, and now, again, h of lambda 1, lambda 3 is loose, abstractly, if you forget the other ones. But the important thing is that it's loose in the complement of h of lambda 1, lambda 2. This loose chart over here is away from this green Legendrian. And of course, lambda 1 is going through both of their loose charts. Not the complement of lambda 1. Okay, so what does this mean? So in general, if you have more Legendrians, what this implies is h of lambda 1, lambda 2 and the k is flexible. And it's flexible because the next Legendrian is loose in the complement of all the previous ones. And when we're attaching the handles, we just care if it's loose in the new contact manifold. So it's flexible because h of lambda 1, lambda I is loose in the complement of previous Legendrians. So in this case, I mean h of lambda 3 is loose in the complement of this one. So I first attach a handle to this Legendrian, which is loose, and then I attach and then in that new contact manifold, this will be a Legendrian, and it will still be loose because this zigzag is away from this green Legendrian. So that's why this is flexible. Let me call this V flex. And finally, W is homotopic to V flex plus this handle along lambda. And remember, lambda is going through the loose charts of all of the other ones. So even though h of lambda 1 through lambda k form a loose link, once you add the last one in, the whole thing is not loose, and it somehow remembers all of the symplectic topology which was there in the first place. Yeah, so and then lambda 1 passes through loose charts of previous ones, of all the other Legendrians. So that's the proof of, where's the statement? Yeah, so that's the proof of this slightly weaker statement where you have W homotopic to V flex plus a single handle, right? That's this statement. For the stronger statement where you have W is homotopic to W flex plus a minus 1 handle plus a n handle, what you need to do is you need to first introduce two canceling handles. So first you write W as W sub plus all of these handles that it originally had, and then you introduce two canceling handles, symplectically canceling, and then you handle slide everything over lambda 0. You actually have to do it algebraically. You have to do it twice with opposite sign. But it's a very similar argument to this, so I won't go into that. So how much? Do I have 7 minutes? Or? Okay. So yeah, so that's essentially the proof of the main theorem. But in the remaining time, I'd like to give some maybe algebraic interpretation of this result, which maybe will provide more intuition to some people. So, let's see. Okay. So I'm going to try to explain why this result should hold from the point of view of Fukai categories, like why should you expect this flexible subdomain plus a single handle. Let me just do the case of two critical handles, two handles of index n, and I'm going to use x to denote a Weinstein subdomain instead of w now. But you have now just two handles and attached along lambda 1 and lambda 2, and these handles, they have cocores, as I said before, and the cocores actually turn out to be Lagrangian because the handles have index n, and they're Lagrangian disks, which I'll denote by C1 and C2, and they're objects of the wrapped Fukai category of X. So this has objects, say closed exact Lagrangians or exact Lagrangians with Legendre boundary, but anyway, C1 and C2 are objects of this category, and it's symplectic invariant of X. Now, recall when we handle slide, we need a chart where the Legendrians lambda 1 and lambda 2 look parallel. So we need a chart where they look like this, say. This is lambda 1 and lambda 2. And actually, when you have two Legendrians that look like this, there's a Reb chord, so you'll denote by gamma, going between lambda 1 and lambda 2. So lambda 1 and lambda 2, and you can make the action of gamma arbitrarily small, and it's between two different Legendrians, so actually d of gamma is 0. So it's a cycle, defines a class in Legendrian contact homology of this link. And Bourgeois, Acombe, Ashberg, they showed that this Legendrian algebra is actually the wrapped Floor homology between the two cocores. So they have the surgery formula that says that this invariant of the attaching spheres knows about this Floor theoretic invariant of the cocores. And this is precisely the morphism space in the wrapped Fukai category. So okay. But now we want to handle slide, say, lambda 2 over lambda 1. So X is now Weinstein homotopic to subcritical domain plus the handle along lambda 1 plus the handle attached along this handle slid Legendrian. And so this is a new presentation for X. Actually, the cocores of this presentation are different. So it has, or these handles have different cocores once you identify the domains. So C2, so C1 is the cocore of this handle, and C2 is the cocore of this handle. So C2 is actually equal to, or C2 tilde is actually equal to C2, but C1 tilde, so topologically it's just a boundary connected sum of C1 and C2, but in the Fukai category it's the cone of a map from C1 to C2. And what is this map? Well, it's precisely gamma when you consider it as a morphism between C1 and C2. So this equivalence here is due to Ganatra, Pardon, and Shende, and I'm told they will appear in their next paper. But the point is that if gamma is 0, then C1 tilde is just the cone of a zero morphism. So it's, in the phi category, it's just the direct sum of C1 and C2. And so in the X. Now, okay, again, the point is we're trying to understand this subdomain, this W sub plus this handle slit handle. And we were trying to find an algebraic reason why this is flexible or algebraically flexible or something. But this subdomain is just, so this is just the second handle in this presentation, and that's the same as starting with X and removing the co-core of the first handle. If you remove the co-core of the first handle, you're removing the first handle, you're left with the second handle. Now, it turns out that this Weinstein domain has the same wrapped Fukui category it turns out that the wrapped Fukui category of this domain only depends on C1 tilde as an object of the wrapped Fukui category of X. But C1 tilde is equivalent to C1 direct sum C2. And this is the same thing as the disjoint union of C1 and C2. So this is the same thing as just X minus C1 disjoint union C2. And well, here I've removed both of the co-cores of the presentation, and I'm now down to just the subcritical domain, which has zero Fukui category. And this statement is due to Zach Sylvan and also the first paper, I believe, of Ganatra, Pardon, Shende. Okay, so the point is that the wrapped Fukui category of this subdomain, which is the one we're interested in, is, okay, I have to take derived Fukui categories, is equivalent to the wrapped Fukui category of the subcritical domain. But like I said, subcritical domains, they have vanishing symplectic homology. This is a trivial category, so this category is trivial. So that's one way to see that this subdomain is algebraically flexible. But we need to take a Reb chord, which gives rise to a zero morphism. So that's actually an important condition. I didn't give any examples, but there's ways to do handle slides so that the subdomains you get are not flexible. But it turns out that when you, like I said, if you do this, you have this local model, and now you add this Reidemeister twist. I believe that this is a new Reb chord over here, and this Reb chord is now actually zero in the wrapped Fukui category. This Reb chord was arbitrarily a Reb chord. It might not have been zero, but this one, I believe, is killed by this Reb. So there's a whole family of Reb chords here. They break up into two Reb chords, and I think one of them kills this Reb chord down here. So, and that would kind of give an algebraic explanation for why we're getting something flexible. So let me stop there. The LS. What is the?
Covered by the consent, it is included the boundary number of critical points any function.
Sorry, can you say it again?
If you would have found below the number of critical points for a function, instead of Morse, from topology, which is minimal number of open sets and an open covers, the open sets includes no.
Yeah.
But that's a question in the Weinstein
Okay.
setting.
Like, what's the nominal open cover of a Weinstein domain? Is that the question?
It's removing the word Morse.
Okay. I don't know if this answers your question, but something that is true is that any exotic Weinstein ball, it can be covered by two Weinstein domains which are homotopic to the standard ball. So, but that essentially follows from the main theorem. Yeah, I don't really know how to do anything beyond the Weinstein setting. You really, seems like you have to use the Weinstein structure and use these moves. But. Okay.